Hello everyone and welcome. In today's video, we're gonna take a deep dive into the world of vaults. But not the vault you find in banks where there is money and calls. We are talking about HashiCorp Vault, also known as Hash Vault, a powerful tool designed to securely manage sensitive data. In this session, we're going to explore how to install Hash Vault within a Kubernetes cluster and how to connect all the pieces together. Our goal will be to access a vault secret from a pod running a Spring Boot application within our cluster. So let's get started. First, let's define what is Hash Vault. Hash Vault is not just any tool, it's an identity-based secret and encryption management system. Think of a secret as anything you want to keep under tight control, such as IP keys, password, and certificates. It was developed by HashiCorp, the same company that brought us Terraform and Packer, and Vault has been an open source project since the first release back in April 2015. So why do we need Vault? First, because it is a super secure digital safe. Imagine you're having a bunch of keys, really important keys that you use to access your online services or your application. You wouldn't want to just leave these keys lying around. Vault acts like a super secure safe where you can store all these keys, or secret in a technical term like token, password, and certificates. Second, because it provides a controlled access. Vault doesn't just store the secrets, it also controls who can get to them. It's like having a security guard who checks if someone has the right ID before letting them get the key out of the safe. Another interesting feature when using Hash Vault is secret rotation. Some secret can be set to change automatically after a certain time. This is like if you had a magic key that changed its shapes every day. So even if someone copied it, they couldn't use it forever. Vault can also be used to encrypt data. So even if someone intercepts a message, they couldn't understand it without the special key to decrypt it. Hash Vault keeps log of who took which key and when, like a sign-out sheet. And it's great to keep a track of who accessed what, which is really important in businesses for security reasons. Lastly, Vault is meant to be highly available. So this is like a safe that's always accessible. And this is really important because businesses that operate all the time cannot afford to have their safe closed. So let's start by installing our environment. First up, we're going to set up Minikube. If you're using a Mac, we'll find Homebrew really handy for this. And for those on Windows, Chocolate is a great option. But before we dive into the commands, make sure you've got either Helm or Chocolate installed on your system. So here on Mac, I'm using brew install Minikube. Once finished, I will use brew install Helm. Now let's clear up our command line interface to get started. We're going to kick things off by launching our Kubernetes cluster, and we'll do that with the Minikube start command. Once that's done, open a new CLI window. Here we'll bring up the Minikube dashboard. This is where the magic happens. Our Kubernetes cluster is now running locally on our machine. Next step, installing Vault using Helm. Let's head over to artifacthub.io and search for Vault. Hit the install and copy the first command. This is going to add the HashiCorp repository to our local Helm repositories. Alright, now pass the second command into your terminal. Here we are going to include the namespace option, setting it to Vault, and add --create -namespace. This neatly set up the Vault Kubernetes object in a brand new Vault namespace. Once the installation is complete, let's head back to our dashboard. You might notice that workload status showing pending as everything is still setting up. Take a peek at the pod section and you will see Vault-0 up and running. Alright, let's do something cool now. We're going to execute a terminal inside the Vault-0 pod, and we'll run the command vault-ash to display the help information for HashiCorp Vault. If everything goes smoothly, it means Vault is correctly installed and operational within this pod. So back to our terminal, let's set up a network tunnel to forward traffic between our local machine and the Vault pod. We'll use the kubecontrol port forward command for this. Perfect, now let's access the localhost URL printed down here. Now with our network set up, this will open the Vault dashboard for our pod running on our Kubernetes cluster. As you can see here, we're having a form allowing us to specify two important values, key shares and the key threshold. When initializing HashiCorp Vault, the master key is split into multiple key shares, and a key threshold is set, determining the minimum number of shares required to reconstruct the master key for accessing Vault's contents. Let's take an example to illustrate this concept. Imagine we have set up our vault with 4 key shares. Think of them as unique keys, like a green, a black, a red, and a blue. We've also set up a key threshold of 3. This setup means that to unseal our vault, we need at least 3 of these key shares. For instance, if we have the green, red, and blue key, we can successfully unseal the vault. It's like a security protocol where multiple keys are needed to unlock a treasure chest. In our case, the treasure chest being our vault. For the purpose of our tutorial, we're going to keep things simple. We'll choose one for each of those keys. After we press initialize, Vault will give us 2 keys. The first is the root token, which is essentially our master key for accessing Vault as an administrator. And the second is the sealing and unsealing key. Vault starts off in a sealed state for security reasons. So we'll use the unsealing key we just downloaded. Once Vault is unsealed, we'll then use the root token to log in to the Vault dashboard. This dashboard gives us a high-level view of our Vault deployment. As you can see on the dashboard, there is a secret engine section. This is where we can store and manage our secret within Vault. And there is also an access section, which is for enabling different authentication methods. Right now, we only have the token authentication enabled, which relates to our root token authentication. But hang tight, later in this tutorial, we're going to add a new method to enable Kubernetes authentication. Another great feature we have at our disposal is the browser CLI. This tool allows us to execute Vault commands directly from the browser. Now, let's shift our focus back to the Kubernetes dashboard to check on the status of our Vault object within the Vault namespace. As you can see, everything is showing up in green, which is a great sign. It means that our Vault deployment has been successful and everything functioning as it should. Let's create our first secret in Vault. Head to Secret Engine, then click Enable New Engine, and choose KV for key value. Enable the engine with the default settings. Now let's add a new secret. We'll click on Create Secret, name the path My App, and enter 2 pieces of information, username and password. After you hit save, our first secret is all set up in Vault. We've got our Kubernetes cluster running with Minikube and installed Vault in the Vault namespace using Helm. We've also added a username and a password as secret to Vault, laying a solid foundation for secret management. Next, we're going to create our Spring Boot application. We'll go to Spring Initializer, a web tool for quickly generating a Spring Boot project. We'll choose Maven for build configuration, but you can stick with Gradle if you prefer. Set the group name to com.hvault.app and the artifact to hvault.app. For Vault integration, we need to specify some dependencies. Add Spring Boot DevTools, Lombok, Vault, configuration, and Spring Boot actuator as well. Once added, generate and download the project. Next, open the project in IntelliJ or your preferred IDE and clean compile it using Maven. Then I will switch from the application.properties to application.yaml. This is a pure personal preference. Feel free to keep the original format. Now let's set up our Vault connection. In application.yaml under Spring Cloud Vault URI, input the Vault URL, which is localhost on port 8200. Specifying the complete URL make it unnecessary to add the hosts and the port separately. For authentication, we'll configure it to use token-based authentication. This allows our Spring Boot app to connect to Vault using a token. Also, enable the key value engine by setting enable to true here. The last step is to configure Spring configure import to Vault // Spring Cloud Vault will then mount Vault's configuration data as a property source in our app's environment, allowing us to access Vault secret data through our app's environment properties. And don't forget to add the root token we downloaded earlier to our configuration under the Vault token. To verify our setup, we'll start our Spring Boot application configured with Vault. The application should automatically inject the Vault secrets into its environment variables. To confirm this, we'll enable the env and the have endpoint in our application.yaml under the management endpoint section. This allows us to access this endpoint for monitoring once the application is running. After updating the configuration, restart the application to ensure the changes take effect. Let's open localhost on port 8080/actuator/have. It's up, which is great. Next, we'll look at /actuator/env. This shows us the application's current environment properties. However, our secret section appears empty. So to populate it with our Vault secrets, we need to correctly set the path in our HashiVault configuration. We'll add the KV backend property set to KV and an application name property set to my app. And after restarting the app, you can see our secret section now contains the password and the username properties, matching the path properties of our secret in Vault. Vault uses unique paths for each secret, enhancing ease of management and security. This approach prevents the confusion and risk of storing multiple secrets together, making it easier and safer to handle sensitive data. Let's return to our application where we aim to access and display the Vault properties. For this, we'll create a new configuration class named Vault Config, which will include properties for the username and the password. We'll annotate this class with the @configuration properties and @configuration, and we'll also use the @data annotation to generate getters and setters. Next, in our HashiVault application, we'll inject the configuration. We'll also implement the command line runner interface and its run method to log the username and the password as the application starts. I'll be adding a few simple log statements for this purpose, nothing too complex. Next, we'll create our Docker file to build a Docker image for use in our Kubernetes cluster. We'll start with the base image OpenJDK:17, aligning with our use of Java 17 in this application. Before proceeding, ensure to execute a clean package on our project to generate the jar file. In the Docker file, I'll copy the jar into the image as app.jar. Then I will set the entry point to java-jar/app.jar to run our application simply. Once our Docker file is ready, we'll build the image. I will tag it here as Vault and then push it to a public Docker image registry. Back in our terminal, let's create a namespace named app for running our application pod. Following this, we'll set up a new deployment named Vault App Demo. So now let's return to our Kubernetes dashboard and switch to the newly created app namespace. To deploy our application, click the plus button in the top right corner and create a new deployment. We'll use the container image we just pushed to the car hub. In my case, it's HashiVault:\latest, and make sure to use your own Docker Hub ID as the prefix for the image name. So after passing the container image reference, we'll start the deployment and wait a few seconds for our HashiVault app demo to start up. When everything is ready, we can go check the log of our pods. And here, as you can see, we have an error, an HTTP host connect exception. This indicates that there is a problem connecting to the Vault server. This localhost endpoint worked locally, but it fails in Kubernetes, as the Vault pod is running in a different namespace. So to resolve this, let's first verify if there is a service in the Vault namespace exposing the Vault pod. So let's go check under the services section. Here we see that we have a Vault service with an internal endpoint vault.vault:8200. This is the endpoint we need to configure our application to reach the Vault pod in Kubernetes. So first, let's verify the connectivity by returning to our Spring Boot application namespace. We'll open a terminal within our app pod and we'll use curl to reach the Vault service endpoint. We have a response which confirms that our app can indeed communicate with the Vault server. Next, in Vault dashboard under secret engine, we locate our stored secret and we'll use this simple command for retrieving the secret via terminal. So next, let's pass it to our terminal and we'll replace localhost with vault.vault, which is the endpoint of the service exposing the Vault in our Kubernetes cluster. Also, we need to include our root token in the header for authentication, and then we'll execute this command. Now, as you can see, we successfully retrieved the output containing the username and the password stored in Vault. After setting up our HashiVault in Kubernetes within the Vault namespace, we just added a Spring Boot application to a separate app namespace. Initially, our application used a local endpoint, which was ineffective for reaching Vault in a Kubernetes setup. To address this, we tested the connection by executing a terminal command within our app pod. This command requested secret from a specific path in Vault and included a token for authentication. Vault then validated the token and, recognizing our app authorization, as we used here the root token, responded with the requested secrets. You should know that using the root token with Vault is not recommended due to security risks. Instead, we should enable Kubernetes authentication. So let's access our Vault pod and execute a terminal command. Login using the Vault login command and pass the root token. Then press enter. To enable Kubernetes authentication, execute the Vault auth enable Kubernetes command. Now, if we check the Vault dashboard, we'll notice that Kubernetes authentication has been added to the list of methods. To complete this setup, we need the Kubernetes hostname, its port, and the Kubernetes certificate authority certificate. In our terminal command line, let's echo the variable Kubernetes service host, and we'll also echo the variable Kubernetes service port. As we've successfully enabled Kubernetes authentication, let's move on to configure it using the command line terminal. It is crucial for Vault to have access to the Kubernetes host and the ca.crt file. These are necessary to establish a secure HTTPS connection between the Vault server and the Kubernetes pods. So now let's move on to configure our Kubernetes authentication using the command line terminal. For this, we'll need to use the command vault write auth/kubernetes/config. This command is our key to editing the configuration file for the Kubernetes authentication we just enabled. Next, we need to provide the Kubernetes host and its port. Remember the variable we echoed earlier. That's what we'll use here. You might be wondering how to configure this certificate within Vault. Well, it's quite straightforward. This certificate is automatically configured into the Vault when using the vault write command. Alright, now that we have a good grasp of enabling and configuring Kubernetes authentication via the command line, let's explore how to accomplish the same using the Vault user interface. This approach can be more intuitive for those who prefer graphical interfaces. Let's dive in. First, we need to return to our Vault dashboard. Once there, navigate to Access and then to Secret Engine. Our goal here is to enable a new method. So go ahead and select Kubernetes. I'm going to name this method Kubernetes 2 because we already have a Kubernetes method that we set up earlier through the Vault CLI. Now we need the Kubernetes certificate to proceed. To get this, let's switch back to our terminal. Here we're going to list the files located under /var/secrets/kubernetes.io/service account. There is a long-running service account that is mounted under this directory, which contains the three following files. ci.crt, which is the certificate file we need for HTTP access. Namespace, the file holds the namespace scope of the associated token, and the token, which is the service account token used for authentication. We can simply print out the certificate right from the terminal. This is the same certificate you would find in the Kubernetes configuration, which can be accessed using the kubectl command, as shown in the terminal screen. Once we have this file, we can easily pass it into the relevant field in our Kubernetes 2 setup. And of course, we'll also need to specify the Kubernetes host and its port that we can copy from the variables we echoed earlier. Since we previously configured the Kubernetes authentication method using the command line interface, there is no need to have a duplicate setup. We're going to remove this Kubernetes 2 authentication we just created. The next step is to create a role for our Kubernetes authentication in Vault. So click on Create Role and name it Role Test. Then set the alias name as service_account_UID. We'll use a wildcard for the bound service account. The use of a wildcard here means specific service accounts don't need to be matched. And then we'll bind this role to the app Kubernetes namespace. This ensures that any pod trying to authenticate and access stored secret must be deployed within this namespace. With these settings, our role test is now created and correctly configured. This setup is ideal for enabling our Spring Boot application to connect to Vault. Now let's proceed to test this configuration. We'll engage with our Kubernetes cluster by switching to the app namespace, and we initiate a terminal session in our Spring Boot pod. This pod contains a short-lived token located at /var/run/secret/kubernetes.io/service account/token, which we'll use to connect to Vault. Each time a new pod is launched, Kubernetes Token Request API generates a new token. To verify our Spring Boot's Vault connection, we'll execute an HTTP POST request to Vault. This request will carry the aforementioned token in its payload and specify the previously established role test. The request is directed to the internal Vault service at vault.vault:8200/v1/auth/kubernetes/login, located within the Vault Kubernetes namespace. And here we got a permission denied error. And this is because the token required for authentication was not specified in the request. So let's copy paste it and try again. The revised response we received is a clear indication of our successful connection to Vault, achieved through the Kubernetes authentication engine. This process involved authenticating using the role test that we had previously established. This successful authentication is not just a confirmation of effective communication between our pod and Vault, but it also signifies that our pod has been correctly authorized under the designated role. Significantly, the payload returned from Vault includes a client token. This token is a crucial component for our ongoing interactions with Vault, as it allows us to securely communicate with the Vault server. With this token, we can access the secrets stored in Vault that are associated with our role test. To properly set up our Spring Boot application for Kubernetes authentication, we will update the application.yaml. We'll switch from token-based authentication to Kubernetes. This change involves removing the token and updating the host to point to our Vault service, vault.vault, aligning with our app's deployment in the Kubernetes cluster. Additionally, since we're using the full URI, we'll eliminate the separate host and the port field for a cleaner configuration. You can also add the service account token, but there is no need to explicitly specify it. Kubernetes authentication automatically locates the token from the standard pod path /var/run/secret /kubernetes.io/service account/token. Since this path is the default location, we can simplify our setup by removing any specific references to the service account token in our configuration. For our Kubernetes authentication with Vault, it's important to specify the role test under the Kubernetes role configuration. This aligns with the login command we attempted earlier and ensures proper authentication with Vault. Next steps involve packaging our project using Maven Clean package, building the Docker image from our Docker file here, and then pushing it to the Docker registry. Since we haven't altered the image name or tag, updating our deployment is straightforward. We simply need to restart the deployment or delete the existing pod, prompting Kubernetes to create a new pod using updated image. So once the pod is created, let's inspect its logs. As observed here, there is an exception with a 403 forbidden status, accompanied by a message indicating that the Vault location kv/myapp is not resolvable, signifying a permission denial. This indicates our current unauthorized status to access the earlier stored secret. Alright, let's now link a policy to our role test. Head over to the Vault dashboard and in the left tab, find and click on policies. Here we are going to create a new ACL policy. I will name it app policy. Now let's make this easy. Click on example template here to bring up a policy we can modify. We'll use the first section as our base. Copy this section and we'll make a couple of quick edits. Change the path to kv/data/myapp. This matches where our secret is stored. And for capabilities, we'll set them to just read and list. We don't need to update this secret with this policy. So that's all we require. Once we've made these changes, hit create policy to save it. One last tip, the policy path should be the same as where your secret myapp is. Just a reminder, remove the /v1 prefix in the policy path, it's not needed. And there you have it, a new policy perfectly set up for our role test. Perfect, now that our policy is ready, the next step is to attach it to our role test. So first, click on authentication methods on the Vault dashboard. Here, select Kubernetes, that's where our role test is located, and click to edit this role. Scroll down to the bottom of the screen until you find the token section. This is where we specify the policies for generated tokens. In the field for generated tokens policies, add the policy we just created. Remember, we named it app policy. After we've added our new policy, hit save, and then you have it. Our policy is now successfully linked to our role test and we are all set up. Alright, let's switch gears back to our Kubernetes dashboard. Our next move is to delete the existing pod. Why? Because we want Kubernetes to create a new one. This new pod will authenticate with Vault using our role test, which now has the app policy attached. Once it's up, let's dive into the pod logs. Now, as you look at the logs, we'll notice something different this time. We should see an output displaying a username and a password. These credentials are directly fetched from our Vault secret thanks to our newly set up authentication and policy. It's that seamless integration in action. Let's take a moment to recap the process we followed. This overview will help you get a clear picture of how we've integrated Kubernetes authentication with Vault for our Spring Boot application. First up, our pod on the left side of the diagram will authenticate with Vault. It uses the token generated by the Kubernetes Token Request API. which, as we discussed, is mounted on a specific path in the pod. Additionally, the pod communicates the role we configured in the application.yaml file running within it. Once Vault receives the authentication request, it moves to validate the token. This validation is carried out externally using the Kubernetes Token Review API. Vault sends the token to the API, which then validates it. If valid, the API returns a success response along with the namespace and service account details linked to the token. Vault then attempts to match this information with the configurations set in our role test role. If there is a successful match, Vault authorizes the request and sends back a barrier token to the pod. This token is tied to an authorization level defined by the policy attached to the received role. Finally, our pod can use this barrier token to request secret from Vault, all while adhering to the policy constraints of the role it's authenticated under. This completes the secure, seamless integration between our Kubernetes deployed pod and Vault. So as we wrap up our tutorial today, I hope you found it informative and useful for setting up a Kubernetes authentication with Vault with a Spring Boot application. If you have any comment or feedback, please feel free to leave them in the comment section below. And don't forget to like and subscribe to the channel if you like more content like this. Thank you for watching and see you in the next tutorial.